And we have a vulnerability research lead, Fabio Pagani, on the stage as well. Actually, we have a pretty interesting presentation for you. Good afternoon, DistrictCon. It's our first DistrictCon, and actually it says first, but I think it started from zero. Our presentation will include everything what you can see on the title of this slide. It will be new, two freshly disclosed CVEs with base management controller from Supermicro. And these two actually quite interesting because it will be leading for persistence on base management controller. And who is not familiar, base management controllers are keys from the castle in the data centers world. So we will walk you through many different things. But more importantly, we'll show you the journey and problems on the different shades of the firmware, but mostly focusing on enterprise-grade devices and critical infrastructure. So this research, it's been done by binary research team. A lot of members been involved. And actually, some of the data you will be seeing on these slides includes about like 4 years of collecting the data and presenting this data to different conferences, and we already disclosed about maybe close to 1,000 different security issues related to the firmware world. And let's start. So I think like one of the, I think I skipped one of the slides. So why firmware it is important? You just seen the presentation by Natasha and Project Zero colleagues, and they've been focused on mobile stack. And you can see a lot of mitigations. You can see a lot of things which has basically been preventing exploitation. That's not very common in firmware world when we're talking about enterprise devices. And unfortunately, a lot of exploitation chains, it's quite simple, it's easy to exploit. And code complexity is growing exponentially in this world because of the complexity of new devices, because of the modern artificial intelligence stacks, and how these artificial intelligence stacks need to be empowered by modern compute. You can see basically comparison about complexity on the different code bases. But when I started looking first on UEFI-based devices back maybe 15 years ago, the number of lines of the code on these firmwares has been about like maybe 1 million. Now it's beyond 10, and it's growing. So basically, what we will be talking on this research, it's about fragile ecosystem of enterprise devices, critical infrastructure, and how it is affecting actually all of you. We will start with LogoFAIL. And LogoFAIL, this vulnerability we disclosed at Black Hat Europe back to 2023. What's interesting about this issue specifically, it's been found by simple fuzzing with an AF file, and we've been surprised. First, we extracted the parser from one of the firmware, and I believe we started with American Megatrends and Phoenix, and we realized actually this image parsing libraries never get updated for 15 years, and obviously use old parsers, which is contain a lot of issues, but most importantly, it's never get an updates, not security updates, maybe functional updates, but it's kind of a fork of the library. And we figured out like it's actually not a single issue. It's a class of the problems affecting the entire ecosystem. Fabio.
Yeah, sure. So just to get a little bit more a sense of what exploit for LogoFAIL looks like, this is how we developed a POC. From the operating system, you can store a malformed image on the ESP, which is a partition on the disk, or in the environment variable, in a place where basically the UEFI firmware will look for the logo. Then you just reboot the system, the UEFI firmware will start executing, and then eventually we'll try to parse the logo because it wants to display it on the screen. And at this point, the bug will be triggered, and we can exploit the vulnerability. And so for our POC, we actually were able to turn an integer overflow to heap overflow, and eventually to get arbitrary code execution during Dixie, during the boot process. There are also other vulnerabilities which are not related to the fact that UEFI firmware is written in a C language, so it's written in a safe language. There are a bunch of different mechanisms that are proper of UEFI which can cause bugs, which can introduce bugs if they are not used properly. For example, I just want to speak more about the third one in this table, what we call the pointer via variable memory write. In this case, what's happening is that UEFI firmware reads the content of an NVRAM variable, which can be controlled generally by an attacker, and then just uses it as a target for memory writes. And this, of course, gives an attacker primitive to modify and tamper memory. I will show you in a second an example of this. As you can see, most of these vulnerabilities have actually very high CVSS score, and also there is quite a bunch of different CWEs. We have out-of-bounds write, out-of-bounds reads, we can untrusted pointer the reference. I mean, there is a quite of variety of issues that can happen when these mechanisms are not used. There is also a sort of a class of vulnerabilities which we treat separately from the rest, and those are the vulnerabilities which affect secure boot and which impact the chain of trust.
Yeah, I think like always bypassing secure boot on enterprise devices has been kind of an opening doors for bootkits, and we will talk about the bootkits and show some cool demos for bypassing EDR systems and endpoint security. But thing is, like what we found in 2024, yes, PK it's been actually very interesting. So we found, think about you live in an apartment complex, and all the doors has the same lock. And you found the key, you can open all the doors. And now think about the devices. We found the key, which can affect almost every single device in the ecosystem. It's kind of been a holy grail for bypassing secure boot. When we found this, we actually didn't realize how big it is. It's taken us some time to figure it out because we cannot believe that is actually can be a truth. And you can look our presentation, you can look demos on YouTube on the PK file, but thing is about these problems are not fixed on a lot of end-of-life devices. And PK file could actually affect many of those devices still in nowadays. And Fabio will give you some technical perspective.
Yeah, exactly. So just a little bit of details of what's secure boot. You can just imagine that at the end of the boot process, UEFI firmware has initialized the platform, and it's now ready to give control to the operating system loader. When secure boot is on, UEFI firmware will check that the OS loader is actually legit, that was not tampered with something malicious. And this determination is done based on the content of two databases, DB and DBX, allowed database and forbidden databases. So these two databases are super, super important, right? And there are ways in which these database can be updated. There is different keys. The most important one, you can see at the top of this image, is the platform key. If you own the platform key, you are able to add a key to the middle database, and then eventually to add your own certificates or hashes in the DB. And so basically run whatever untrusted code you want. So one would assume that PK is actually a strong cryptographic key, which is stored properly, and all the nice cryptography things, right? Turns out that we actually found on a bunch of devices a key which was marked as do not trust, okay, which was marked as a test key. Okay, this looks bad, but it's not bad until you don't have the private part of the certificate, right? So we started to search for this string in a database of leaked data, and we actually found it. We found the corresponding certificate with this exact string. And guess what was present in the very same folder where the certificate was? The private part of the certificate, right? The PFX file. And this PFX file has been available on GitHub for 6 months, all right? Completely public. Then, of course, we try to extract the private key with OpenSSL command. We are asked for a password. Maybe, we start to think about maybe we can crack it, maybe there is attacks that can be done. Well, the password, turns out that the password was stored in the same folder in plain text. And not only that, it was also a very simple password. It was ABCD, okay? So, I mean, I know this is fun, right? But this affected like 8 to 10% of devices out there, guys. So I think, it gives sort of a perspective on what's the state of UEFI security and firmware security nowadays. And of course, just, think about how many man-hours, how much money it went to change these keys, to rotate them, and, all this work. This is another vulnerability that we discovered last year, again affecting Secure Boot. It's a vulnerability that's present in a module signed with a Microsoft third-party UEFI certificate. This is a very well-trusted certificate, meaning that it's present in a lot of DBs, because it's the same, for example, certificate that's used to sign shim, so the first stage Linux bootloader, right? And
this module can be reused on different devices as well, right?
Exactly.
So basically, it's being hardware agnostic. You just can take this module and actually use this attack on any device because everybody trusts Microsoft, right?
Yeah. And this is exactly one of these examples, actually, the vulnerability itself of this pointer via variable that I was mentioning before. This signed module will read the content of an NVRAM variable, which can be set from privileged context from the operating system, and we'll blindly trust it. We'll use it for memory writes. We developed, of course, a POC to prove the severity of this finding, and one single write with 0, we prove that's enough to disable Secure Boot and to load eventually second stage malicious bootloader.
Yeah, and basically, not on the technical note about all these disclosures. We disclosed a lot of vulnerabilities, and in many cases, when it's out of the threat model of the vendor, they push them back to fix it. This vulnerability actually will still exist on the devices. And as you could see here, like one of the large enterprise devices vendor, I don't want to disclose the name, but they said like a physical attacks, it's not in scope. But these physical attacks can lead to the persistence. These physical attacks can lead to this reuse of this Microsoft module to actually bypass Secure Boot, install the bootkits, and actually do a lot of harm to your system and gain the long persistence in some critical places of critical infrastructure and enterprise networks. I think from that perspective, we start looking a bit more on how the second stage will looks like. And about the bootkits and rootkits, personally, I have a huge history. It is a book exists called Rootkits and Bootkits. And we dive into a bit how it will looks like in modern days and give you some cool POC on it by fresh Windows 11 and Windows Defender enabled. So this will be a hook for you to follow technical part from Fabio.
Yeah, so before we actually jump into how this specific bootkit that we analyzed work, just a sort of a high-level overview of what the Windows boot process looks like. So again, the UEFI firmware ends the initialization, gives control to the Windows Boot Manager. The Windows Boot Manager is actually reads the boot configuration, verifies some things about the boot environment, and then loads and executes the Windows OS loader. The loader now loads the core operating system files, drivers, the kernel, and a bunch of other things, and then eventually leaves control again to the kernel, which ends the setup and gives control to user space, and then the Windows session starts. So given this high-level overview, it's clear that if we have a bootkit that's running in the UEFI and we want to affect the kernel, we have somehow to jump through all these stages and be able to expand our attack until we reach the kernel. And this is exactly what this bootkit does. This is called Red Lotus. It's open source
Wait a minute, it's written on Rust. It should be secure.
Yeah. It's open source bootkit. It's a research project, but I think it's very nice. It also draws inspiration from Black Lotus, which is the bad guy. And as I said, first step, we exploit a vulnerability. It can be LogoFAIL, it can be picky fail, whatever other vulnerability that gives you code execution during any phase, actually, of the UEFI firmware. So you have arbitrary code execution at the UEFI level. And at this point, you start the bootkit infection chain. This means that what this bootkit does is to load in memory the Windows boot manager and searches with the pattern function, the image arch start boot application function, and then gives control back to the boot process. So at some point, this hook will hit, right? And now we are in the context of the Windows boot manager. When this hook hits, the bootkit searches for other two functions and install another set of hooks. Gives, again, back control to the boot process, and then the first function, the first hook hits. With this hook, the bootkit allocates a buffer and stores there a rootkit kernel driver. With the second hook, again, in the context of the Windows loader, the bootkit will traverse the list of loaded kernel drivers, will find a victim driver, and will patch the entry point to the rootkit, which was just allocated in memory. Again, gives back control to the process, and this time the Windows kernel will execute, and the kernel will initialize the drivers, right? But don't forget that one of them was patched with our own malicious entry point. So the bootkit gains control again over the execution, and at this point, the entire kernel is loaded in memory, and the bootkit reads and searches for a specific function and patches it in the kernel. Yeah, and finally, the process just completes.
I think you need to think, like you need a firmware vulnerability and also bring your own vulnerable driver, assign a driver to the system, and it actually will give you some keys to establish this persistence on any Windows system, even by nowadays. And yeah, look what can happen.
Yeah, this is what actually a combination of a secure boot bypass and with the bootkit looks like on Windows 11. You will see in a second that we are dealing with an up-to-date Windows machine.
Demo been recorded right before this talk, so it's fresh stuff.
And here you will see that secure boot is actually enabled. So in theory, you could not execute any untrusted code during the boot process. We prepare the environment for the secure boot bypass to happen, and finally we reboot the system. So now in a second, you will see that the secure boot bypass runs and that we are able to print some ASCII art just as a proof that we actually were able to execute untrusted code during boot. But we don't stop here, because now it's when the bootkit starts, right? Now the Red Lotus thing takes care of setting all the hooks. And in a second, you will see in the debugger window that the rootkit, the bootkit, it's printing some stuff about all these different hooks that it does. And you will see in a second what's the capability of the rootkit. And this is of allowing an unprivileged process to load an untrusted driver. You see here that we were able to load this driver.sys. Sorry, I wasn't able to stop it on time, but we are able to load basically an untrusted driver from an unprivileged shell, which is of course pretty bad. An untrusted kernel driver, right? So we are now in kernel again. And this is, of course, just one capability that can be implemented by rootkits. There has been this recent presentation at DEF CON where the authors presented the ABIS rootkit, and this has actually more advanced capabilities than Red Lotus.
It's open sourced and it's on GitHub if you're interested to look deeper.
Exactly, exactly. Basically, by having control at the kernel level, this rootkit is able to do, for instance, hide processes, doing direct kernel object manipulation. It can install a keylogger. It can mess with network, it can hide folders with mini filter. I mean, you know the drill, right? Once you have control at the kernel level, you can get very creative on in what you can do. One thing that you can also attack is ETW, event tracing for Windows. This is a framework which is implemented in Windows that basically records detailed information about what's happening on the system. ETW is at the core of many different EDR solutions, and because it allows the EDR solution to see a lot of what's happening in the system and enable them to do real-time detection and forensic analysis without degrading the system performances. ETW is a kind of a beast, honestly. Just want to give you sort of an idea of what can be done, how this can be attacked. This is something that we presented at Black Hat Europe a few years ago. And you can see that if you have control at the kernel level with an attacker driver, for example, you can mess with a lot of different ETW things. You can, for example, directly mess with the buffers where these events are stored. You can mess with the other drivers which support ETW. I mean, you can get, again, very, very creative. Another thing that you can do, and this is more recent and was presented at Black Hat US, is that you can inject fake events. And this has a couple of implications. First one is that it will make the EDR solution believe that some things happened, while in fact they didn't. And in other cases, it can also be used offensively for creating distractions. What happens is that a lot of cloud-based EDRs, they actually have limits on the amount of events that they can process. So if you start injecting events, you might be able to create blind spots and to basically put some malicious activity in these blind spots. So again, I think here the sort of the message is that with the bootkit, you are eventually able to get into the kernel, and once you're in the kernel, it's sort of game over.
Yeah, I think ETW has been created for observability, but that means it's actually collecting a lot of events and have a lot of power in the system. It's why it's good for forensics, but it's also good for a lot of other things in terms of offensive side of it. And look, our presentation from Black Hat US 2022. So if you're interested in more details, it's been kind of a deep dive on ETW for offensive direction. So let's talk about ecosystem and how at scale this problem actually reflects to the entire ecosystem of the firmware world, mainly for UEFI. And we actually collect a lot of data over the past 5 years. And this research on this data, it's been including about 80,000 different firmware, including famous enterprise vendors from the client, server, and embedded ecosystems from HP, Intel, Supermicro, Lenovo, Dell, and many, many others. So basically, you can see the number of the issues is actually growing. One of the most important things we did, and also this data set probably including a lot of end-of-life devices as well, because actually support Windows, it's quite small for many vendors. It's obviously 2 years. Then it is a kind of like a support for special issues, which is basically high critical. And after 3 years, it's very rare without special SLAs, the support for the devices is actually exist. And specifically on client computing side, if we go to the gamer computing world, it's even worse. And as example, sometimes you could see for the entire life of the device, it could be 3, 4, or 5 updates for like many years. And this is, shows the entire problem and fragility of ecosystem. And it's why it's actually we want to pay attention specifically at DistrictCon for you guys on about this problem and scale of this problem, because we believe it requires a change on the policy side, on the technical side, how these things are handled, and fixes side, because sometimes timeline to fixing the problem in the firmware world, it can take up to 16 months. And sometimes these issues, it's very easy to exploit, like you've seen before on the demos. And obviously, these timelines doesn't benefit defenders. Sometimes this issue is very easy to fix. It's one line of code or like changing one bit. But basically waiting for 6 months, we're giving attackers very powerful tools to persist in our ecosystem, enterprise networks, critical infrastructure, even in ATMs. And let's dive deeper on this data.
Yeah, so here you can see what the impact of known vulnerabilities. So you can think about that as vulnerabilities that have a CV, which are publicly known on our dataset. I guess you can all see this sort of a mountain in the middle of the plot. And I also saw it when I plotted, and I went to look at the data actually to see why there was this happening. And it turns out that most of these vulnerabilities are actually related to LogoFAIL and PXE-fail. Now, these two vulnerabilities have something in common, and that is that both of them affect the very first parts of the UEFI firmware supply chain. In particular, PXE-fail affects the EDK2 reference implementation, which you can imagine as a very top of the UEFI supply chain, while LogoFAIL impacts the code which was developed by IBVs, which are just one step below, right? Since this, you can just imagine it as a tree, and you can see that these vulnerabilities then are able to sort of trickle down into OEMs, device vendors, and everything which stays downstream. And so they have a huge impact. These two vulnerabilities were disclosed at the end of 2023, and as you can see, they really affected a lot of firmware which was released before that.
Before you start on unknowns, I want to add a bit of color on this particular slide. One of the things we've been focusing for our mission in the company is actually how we can prevent these issues to happen on the development side when developers just building the new firmware or updating it with the new features before they release it to their customers. And we developed the technology when we can detect different classes of the problems. Of course, this is not detecting all the unknown. It's obviously 0 days in the world, but specific classes modeled with abstract interpretation and validating inside of the code with symbolic execution. That's what this graph is about.
Yeah. So again, this is very similar to the other graph, and you can see what's the impact of unknown, this time firmware vulnerabilities. And there is finally the first and last good news of the talk, is that the average number of vulnerabilities is actually decreasing.
After 5 years of disclosing a lot of issues, they finally start fixing SMM callouts.
I went and tried, I also had a closer look at the data. I didn't find any specific reason. What this might be actually related is that, as Alex was mentioning, in 2021 is when we started to massively report hundreds of vulnerability per year. And this might have actually had a nice impact on the UEFI security of the ecosystem, right? Bad news is that the 90% of the firmware that were released in 2025 still contain at least one high severity vulnerability. And again, I will just let that sink in for a second, because this can, and very likely can allow you to bypass secure boot, to get arbitrary code execution during DXE, to mess with SMM, which is another class of vulnerabilities or problems. And so I think the road ahead is still pretty long. And this, of course, is also not passing unobserved by malicious actors. This is a recent finding from September 2025 from ESET researchers that discovered a sample on VirusTotal they call it hybrid PETIA, which is a copycat of the famous PETIA, not PETIA malware. Problem is that this hybrid PETIA is completely implemented, and it will run during the UEFI boot process, and also it includes a bypass for secure boot for outdated system. So it also embeds and has this capability.
Yeah, I think if you look on the statistics of use of firmware originates vulnerabilities, it's more like a state-sponsored actors been using quite a while. But now when basically defenses on operating system get stronger, gamers start using for cheating, but also commodity cyber criminals start also adopting these practices because it's cheaper. It's easier from the perspective of exploitability, and actually in some of these vulnerabilities it's highly reliable, like a picky fail and vulnerability which we disclosed on Microsoft module. It's been basically 99% reliability of exploitation, because exploitation chain been quite easy on this one. This is a cherry on the top of our research. 2 new vulnerabilities on Supermicro devices, basically which is used on enterprise networks and data centers. We're talking about Supermicro ecosystem of the servers and very high profile and expensive devices, including some of the devices for artificial intelligence data centers. Main problem is, like in the industry, not all the vendors have a comprehensive security teams, and sometimes fixing the same of the issues, it takes time. Obviously, we work with Supermicro team to fix these issues after we start discovering them, but all this research, it started with the CVE, which has been found by NVIDIA team. I want to say hello to my former offensive security research team I created at NVIDIA. Obviously, the folks discovered interesting verification bypass. And by request of our customers, we start looking on this issue from perspective of detection, and they can be protected on their ecosystem and data centers. Just to be clear, Supermicro servers, it's one of the most popular one. Also, it's one of the cheapest one, and these 2 data points connect together. So this is a timeline. So NVIDIA discovered first a few issues on the verification process, and what this really means. Bypass of verification process on the firmware update, it's obviously you can modify the firmware update, gain persistence on base management controller, which is responsible for update on UEFI system firmware, FPGA, if it is exists, or ASIC. So basically, it's very impactful vulnerability, and obviously, as I mentioned it at the beginning, it's kind of a keys from the castle on the in the data center world. You can basically get already implanted device if you don't want to, if people don't do in provisioning or basically researching on that, and this is kind of been ridiculous timeline from the perspective how this goes. So first, NVIDIA disclosed. We start looking and we found bypass on this fix during spring of the last year. It is 2 blocks we already disclosed on these issues where we've been talking about these problems. And then basically these issues got fixed, and binary research team, wait a minute, let's look on fixes. It's been already bypassed before, it will be bypassed again, right? So, and we look on the fixes, and it's been inconsistencies on the fixes, and we report 2 new CVEs, basically, I think in September last year, and bring in these new vulnerabilities, especially for DistrictCon, and the timeline on the disclosure with the vendor been exactly today. So let's look how Supermicro-based management controller validation works in general. And Fabio will be in a minute dive deeper on the technical details, but what I really want to cover here, I think you can see multiple mechanisms on basically validating the firmware. One of them an FMAP, and another one, it's basically based on specific region validation. And that's already a red flag from the perspective you have multiple parsers, and it is inconsistency on validation process. It is a complexity increase on your most critical piece of the code, which is responsible for actually rooting the trust on this device. Fabio.
Yeah. So as Alex said, this is what the firmware validation process looks like for Supermicro. The general idea is that once you upload a BMC firmware, this will be parsed, and all the signed region will be concatenated, and the firmware will calculate an hash digest over these regions. And then they use a signed signature. We also come with the update with a public key, which is instead stored on the device. And this is sort of your usual digital signature verification with a public and private key cryptography. And if a signature is OK, then the firmware will be flashed and will be used from now on the device. So now we'll have a closer look at how the firmware map-based validation works. So the firmware map table is crucial for all of these attacks, because this is a table that is used to actually parse the uploaded firmware. The table has multiple entries. Each of them represent a firmware region, and it has where the region starts, the size of the region, and also different attributes, for instance, if the region is signed or not. The firmware map is stored in an actual region of the firmware, which is called PDB-SEC-A. And one thing which is super important is that the PDB-SEC-A region is found by scanning the firmware and searching for a specific pattern. And you will understand in a second why this is actually important. This is just a sort of a view of what the firmware map looks like. As you can see, it's just bunch of regions. We have, for example, the bootloader, the kernel, the rootfs, the PDB-SEC-A, which is the same region which contains the firmware map, and so forth. So what's the initial idea that the NVIDIA threat research team had was to inject a malicious PDB-SEC-A region inside the uploaded firmware. And they placed this region just before the original one. Since this region is searched by pattern matching, by searching for a magic, then the malicious one will be actually found before the actual one, right? And this means that at this point, the validation process will use the firmware map, which is controlled basically by the attackers. And you can see the custom firmware map on the left side of the image. And what they did is that they also did a similar trick with by replacing the original rootfs with a malicious one. In this way, with this PDB-SEC-A region, with this firmware map, the firmware validation process will work, but the different rootfs will be used during boot. And here you can see on the left side that the verification looks good. On the right side, that we are able to print a string just after SBIN init is run as a process. So because we were able to attack the rootfs. So this is the first patch that Supermicro proposed and actually implemented for this problem. They have the two constraints. The first one is that no custom region offset in firmware map are allowed, and only whitelisted offset can be used. The second one is that they place some constraints on which region can actually have the is signed flag. So we thought a little bit about this, and we came up with this attack, which is that we basically took all the original region from the original firmware. We stored all of them together, one after the other, inside the custom BMC firmware, which is the malicious image that will be uploaded. And we injected, once again, a fake PDB-SEC-A region with a firmware map with a single entry, which represents this region. Once again, since we also moved the bootloader in this process, we were able to replace it with a malicious bootloader. And here we'll see in a second what this looks like. We were, in this case, just to prove our POC, we changed the U-boot string, and we added binary research as a marker that we actually were able to execute code, and we used to swap the bootloader. So we sent all of these findings to Supermicro, and Supermicro assigned a CVE and patched this. They added two other constraints. First one is that the offset of the processed PDB-SEC-A must be a specific value, so it cannot be, the PDB-SEC-A cannot be moved around the custom firmware. It needs to be at that specific address, and also that the firmware map should contain at least one region which represents the PDB sec-A. The problem is that they added these two constraints, but they actually removed the previous one. And so we were able, again, to add different entries and to mess with the firmware map and to add them and to add these entries at a custom offset.
Complexity, right?
Yeah, always. Exactly. So just to cut it a little bit short, we were again able to mess with all these regions, with the firmware map, and to swap again the bootloader. And we also have a demo for this attack.
It's a new one, which we're disclosing today.
Yeah, here you see what it looks like. So from the interface of the BMC, you will select the malicious BMC firmware, you hit upload, and then in a second, you will see that the firmware is parsed, everything looks good, there is a version, and we finally load it. And here you will see that we are getting again some output. Remember that we also swapped this time the U-boot, and again we proved that we were able to get the core execution during the boot process again.
Obviously, these issues lead not only persistent on base management controller. As you could see, it could impact host OS, and it's basically game over. If attacker in modern data center ecosystem control base management controllers, if it's no something special on these devices to protect this device, I think you can actually off this system completely on all the directions.
Yeah, so we did again we reported all of our findings to Supermicro, and they finally came up with a final patch, which has a bunch of constraints. We won't go through all of them. We think that these are actually enough for stopping all the different attacks, all these different mess that we just discussed. So there are, though, a few concerns that we have about this final patch. The first one is that for both devices that we tested, the RSA keys used to sign the image were not rotated. They have some checks that prevent firmware downgrade attacks, so we cannot immediately downgrade to a malicious version, or to an unpatched version, but it's something that may arise in the future. And specifically for one device which implements the SIG table validation process, the validation was moved from the OPT environment to a library. And this also, we think that this could allow potential attackers with root privileges on the BMC system to directly mess with the library and bypass the introduced checks.
Yeah, unfortunately, it's what we see with complexity of the code on the system firmware from many perspectives and embedded firmware. It is complexity actually, when you fix in one issues, it's actually opening like a new attack surfaces as well, and it's what Fabio exactly described. Removing module from trusted execution environment, it's actually escalating attack surface quite significantly. And we share all this information with Supermicro, and we validated the patch for them before this talk. So basically, we've been working closely with them on these issues, and hopefully they will follow some of the conclusions we made on our research. And it's been kind of a goodwill from the perspective we don't want these issues to be repeats, but seems from complexity perspective, we cannot guarantee this is not new attack surface being opened, which could be exploitable as well.
So at the beginning of this part, we also mentioned about the SIG table validation, which is complementary to the firmware map. We don't have time to go through it, but it has similar problems. We were able to bypass it. The Supermicro patched it, and we did the same sort of process in parallel. But we have a blog post coming out soon, with all the details also about the firmware map attacks. So stay tuned.
Yeah, we will be releasing the blog post on Monday with all the details on this research. And I think what Fabio said on this slide, it is still some of the directions which could be logged. And it will be great to see on the DistrictCon 2nd, the talk on this topic, guys. I think we'll give you a lot of details and pointers. Don't hesitate to ask the questions. So I think it's a very critical area, and it's actually deserve that deep dive from the community. So that's pretty much it from our talk. And as a conclusion, you can see this has been happening before. It will happen again, but it is a lot of work need to be done on the security side, and even more on the policy side to actually create some directions when the vendors will be acting more responsibly from the perspective of constraints their not properly fixed issues could lead. And specifically in our modern world when we rely a lot on the compute stack, and with all artificial intelligence distribution, it even became way more critical right now. So I will kind of finalize our talk on this note, but the positive side is, as you've seen on our graphs, some of the classes of the issues decreasing, but new ones appears, which is quite concerning. Thank you very much, DistrictCon, and thank you for staying by the end of this presentation. So keep an eye on Binary Research blog. It will be more details coming. Thank you.